In chapter 6, we're looking at projectiles, and in section 6.1, we're looking at horizontal projectiles. Now, what that means is I am taking an object and I'm throwing it horizontally. In these exercises, we're just throwing horizontally. Now, when we get further into the chapter, we're going to stop throwing horizontally and we're going to start throwing at all sorts of angles, but for the moment, we take an object and we throw it horizontally. Now, in order to do that, of course, we're going to have to start at a certain height. And when we throw horizontally, what's going to happen? Well, we're going to ignore air resistance. We're going to keep ignoring air resistance. Sorry, I should just say, when I say throwing, I don't actually literally have to be throwing. It could be firing this thing. It could be, it doesn't have to be an object held in the hand and being thrown. It's any object which is sort of starting to hurtle through the air, initially with a horizontal motion. So what's happening to it? We're ignoring air resistance. So if we ignore air resistance, horizontally, there's nothing to slow this thing down. Vertically, it's being pulled down by gravity. Now, if you imagine this thing was thrown straight towards you, and if you somehow imagine that it can't get bigger as it gets closer as well, what would you see? What you'd see is the object starting, so let's say it's here's the ground, and it's thrown straight towards you starting here. You'd see the object falling towards the ground, wouldn't you? If for some reason you didn't have any depth perception, you couldn't tell if it was coming closer to you and hitting the ground, or if it was just falling straight down and hitting the ground. That's what you would see. Okay, and it turns out that that's exactly what happens. Vertically, it falls in the same way as an object would fall just straight down to the ground. The gravity pulls it downwards. We're not having any air resistance, so it is just gravity that's pulling it downwards. And that happens in exactly the same way for an object that's moving sideways as it does for an object that is still and just falling down. Horizontally, there is no air resistance. It's got an initial velocity, so it just keeps going at that constant speed. So if we have an object where we can ignore air resistance, we can model it as this is what happens. It falls down and it hits the ground. The only thing that stops it moving is hitting the ground. As far as the horizontal motion is concerned, it could just keep going because there is nothing slowing it down. Vertically, it's going to accelerate downwards and hit the ground. Okay, and that's what we've got. My diagrams are getting a bit confused with each other there, aren't they? So it's doing that, and it's just going like that and hitting the ground here. So we think of those two things separately. That means that horizontally, we're applying speed equals distance over time. Okay, it's got a constant speed. So what do you do with the constant speed? You do speed equals distance over time. Now, the way that they like to do that in the book is S equals VT. So displacement equals velocity times time. And we should be using the words displacement and velocity. I'll absolutely agree with that. This is a motion to the right rather than to the left. So it is a vector. So we do need displacement and velocity. That said, I like to think of this as speed equals distance over time. They've got it as displacement equals velocity times time, or distance equals speed times time. Same equation though. So horizontally, that's what we're doing. Vertically, what do we have? Well, we don't have a constant speed, but we do have a constant acceleration. And we've seen questions like this loads and loads of times. It's the Suvat equations, isn't it? U, V, A, S, and T, initial velocity, final velocity, acceleration, distance moved, and time. And so horizontally, we're going to apply this. Vertically, we're going to apply this and the constant acceleration equations, or the Suvat equations, whatever you want to call them. And that really is the essence of this entire chapter. In 10 seconds, split up the motion into horizontal, split up the motion into vertical. In 10 seconds, split the motion into vertical and horizontal motions. Horizontally, the speed is constant. Vertically, the acceleration is constant. So speed equals distance over time and Suvat. And that's it. That's the whole chapter. And we'll just make the questions slightly harder as we go. Let's see practically how we do this then. In example 1, we have a particle projected horizontally at 25 meters per second. So it tells us 25 meters per second in that direction. From a point 78.4 meters, so the distance above the ground is 78.4. Above horizontal surface, find the time taken by the particle to reach the surface and the horizontal distance travelled in that time. Now, what we're getting used to by this point in the A-level mechanics course is, never mind what it's asking us for, what equations can we apply? Well, what we can do is we can say, consider the horizontal motion, displacement equals velocity times time. Displacement, I'm not going to know. What's the displacement from here to here? Not sure what that is. But the velocity is 25. and the time is something else that I don't know. So displacement equals 25 times t, and that's equation number 1. There's nothing else we can do with the horizontal movement. Vertically, what do we have? U, V, A, S, and T. Now vertically, there is no vertical component to the velocity. It starts off moving horizontally, so vertically, it's not moving up or down. Okay, so initial velocity is 0. Final velocity, how fast does it hit the ground? I don't know. Acceleration is 9.8. Now I'm going to decide that upwards is positive, because that, to me, just intuitively makes more sense. We could have upwards being negative, and downwards being positive. With upwards being positive, I'll put acceleration in as minus 9.8. The displacement is going to be, from here down to the ground, is going to be 78.4, and that has to be a negative displacement as well, because I'm accelerating in the negative direction, so I need minus 78.4. And time, I don't know. Now, if you look in the example in the book, they've decided to make downwards positive, so they've got a positive 9.8 and a positive 78.4 in their equations. So, at this point, I've got several things that I could be trying to find. I could be trying to find this s, this horizontal distance here. I could be trying to find the time. Now, this time here and this time here are the same. The time it takes me to move from here to here is the same it takes to move from here to here. Okay, so that t and that t are the same. And then there's this velocity as well, the speed with which it hits the ground. So I've got 3 things that I could possibly be asked for, so there must be 3 equations that I could write down. I've got one of them. What are the other 2? Well, there is the Suvat equation that doesn't involve v. That's s equals ut plus half at squared. And if I filled these things into this equation, then the only thing that we'd be missing would be t, wouldn't it? And the other one would be the Suvat equation that doesn't involve t, which is v squared equals u squared plus 2as. And if I wrote that equation down, the only thing that would be missing would be the v, wouldn't it? I could put the u and the a and the s in. So there's one equation there, there's a second equation there, there's a third equation there. This equation here would tell me the time, and from that time I could find that horizontal displacement. So we're back in the situation of do the first thing we can do the second thing we can do, write down the equations that we've got, and we'll be able to find everything that we need. At this point, I'd go back and look, and it says it wants the time taken for the particle to reach the surface. Okay, so if it wants time taken, this is the equation we said we have to use. So s is minus 78.4, u times t is 0, a half times minus 9.8 times t squared, and I'm going to cheat slightly and just take this then. So if we work that out, that turns out that t equals 4, but we can solve that equation with a calculator, or well, perhaps even without a calculator, who knows. So t equals 4 seconds. Once I know that t equals 4 seconds, what does part B ask me to do? Find the horizontal distance for the time travelled. Well, if it's going for 4 seconds at 25 meters per second, then horizontally it's going to go 4 times 25. In other words, I take this 4 and I substitute into equation 1 here. Okay, and that's the pattern for all of these questions. Do this, do this. Once you've done that, you will have some equations that you can write down, and they will find the things that you want. Now, I'll do a second example in a minute, but that really is the principle. You might even want to stop the video and do example 2 for yourself, and then we'll come back. They can obviously make different things the missing thing. So the missing thing could be the, well, not the A, because that's always going to be 9.8, but they could make the vertical height the thing that we don't know, or they could make the final velocity the thing we're trying to find, or whatever it is, right? We can, or even they could say, well, we don't know what speed we set off at, but we know where we landed, so what was the initial speed, that sort of thing. One point to make before we zip into example 2, though, and this, if you haven't seen it before, is quite a remarkable thing. One of the consequences of this reasoning is if you took to take a gun in one hand and just hold a bullet in the other hand, and you fire a bullet from the gun. Now, that bullet is going to go horizontally, but it is actually, if it doesn't hit anything, it's still going to curve down and hit the ground. And at the same time as you fire the gun, you take the bullet in the other hand and you just drop it. Now, what happens here, look, with a bullet, small object that's moving fast, we can ignore the air resistance, So the bullet that you fire from the gun is going to hit the ground at the same time as the bullet that you drop from the other hand, because what happens vertically is not affected by what's happening horizontally. And when I say we ignore air resistance, the only important bit of the air resistance here is the vertical air resistance, right? As the things are dropping down, is that going to go faster or slower just because it's moving horizontally? And the answer is no, it doesn't go faster or slower moving horizontally. So both that bullet that you fire from the gun and that bullet that you drop from your hand will hit the ground at the same time, okay? Which is quite a remarkable result, but that's the consequence of the reasoning that we're dealing with here. So, example 2. Another example of exactly the same technique. It doesn't matter to me which bits are missing. In this case, it looks like the vertical distance and the horizontal distance are missing. We are projecting with a velocity of 15 meters per second horizontally. So we're going to get this sort of motion, 15 meters per second. I'm going to consider horizontally s equals vt, so speed equals distance over time, as I like to think about it. The displacement we're calling x, the velocity is 15, and it goes at that speed for a certain amount of time. Now in this case, we're not actually hitting the ground, it's just saying this is travelling for 3 seconds. So x equals 15 times 3. Vertically, I've got u, v, a, s, t. Initial velocity vertically is nothing. Final velocity vertically, I don't know. Acceleration, again, I like to make positive upwards, so minus 9.8. Displacement is what they're calling y. The distance is y. I could introduce a negative sign here, and then y will turn out to be positive. It doesn't really matter. I'll leave it in there as a y. And if I get a negative out of my equation, which in this case I would do because y is a displacement in the negative direction, then I'll know that the distance that we're looking for, we just ignore the sign. And then t is the same as the t was up here, so 3. Okay. They're asking us for the horizontal and vertical components of the displacement of the particle after the point of projection. Well, the horizontal component is there, 45. The vertical component is this y here. So I need an equation that doesn't have v in it. So s equals ut plus a half at squared is going to do the job again. So if I write down s equals ut plus 1/2 at squared. Now I'm going to leave you to finish that off from there, or you can follow it through from the book. But it turns out that x equals 45 and the y equals 44. Okay? Now, the next thing it asks us is what's the distance of the particle from the point of projection? So we start here. We know we've gone 45 meters horizontally, and we know we've gone 44 meters vertically. So the distance we want is this distance here. Well, that's just an extra little question, isn't it? That's not too much of a problem. If you just draw that out, it's a Pythagoras theorem question. Okay, so the tricky bit was horizontal motion, vertical motion. Consider them separately, and that will get you where you're trying to go. Okay, good luck with exercise 6A.